So the goal today is to explain what I guess this lecture is more like a survey. There's not much sort of proof. So I'll talk about Galois representations appearing in geometry. So I'll start with the KVA field, and my notation X is proper smooth variety over K. I'll introduce reintroduce probably the étale cohomology. In the sense that I'm not going to define what étale cohomology is. So next semester, Professor Yuan will give a course on what étale cohomology is. For our purpose, we just want to work with what like étale cohomology without knowing what it is. I'll give you some. Hopefully, I will give you enough sense of what it looks like, and then we can just talk about it. Okay. I'm going to fix an L different from the characteristic of K. From this, I'm going to define so-called. So this will give us a étale cohomology. This étale cohomology is sort of non-zero only when the degree is between 0 and twice of the dimension of X. And this one carries a Galois group action of the Galois group of K. Okay? So at this moment, just think of it as a QL vector space. Maybe I should say this is a QL vector space. It's a finite dimensional, excuse me, QL vector space. Hopefully the next one will give you some sense of what it is. So when, at least when characteristic of K is 0, let's assume there's no issue with cardinality. With the cardinality of K. So I can usually embed K into C. Okay? If K is not too large, in the sense that there's no set theoretical issues, I can always embed the characteristic 0 field to C. Then this sort of mysterious étale cohomology of X is isomorphic to just do the usual singular cohomology. I base chain from K along this embedding to C, or maybe spec C, whatever. And when I base chain from K to C, I get a complex variety, a smooth complex variety and proper. So I will get a what's it called? A compact, a compact complex manifold, and with no boundary. So I take sort of analytic part of it, namely. So I really think of it as a sort of topological manifold, and then for that I can take the singular cohomology, and I tensor that with QL coefficients. Okay, so what étale cohomology is, again, what étale cohomology is you can. So the way we work with it is usually just think of it as sort of singular cohomology of a variety. And in general, if our variety is over a field, general field K, of course we can't really think about sort of topology. But even so, when we draw pictures of this, what this variety is, we just sort of draw it as if we're working with over C. So I guess by this I want to convey that don't be scared of étale cohomology. Just think of it as a singular cohomology when you work with it. Okay? There's not much sort of pathological situations. Or at least somehow for our discussions, there are not much pathological situations. Everything somehow we know about this sort of, usual topology or usual cohomology theory works sort of equally for étale cohomologies. So to give you some additional information about this étale cohomology, if X is a curve, if f is geometrically connected, meaning that our base chain X to separable closure is connected, then because I assume my X is proper smooth, H0 étale of X and the top cohomology of X. Oh, sorry. My bad. Separate them. So this is one dimensional. And the top cohomology also one dimensional, except that there's one key difference between singular cohomology and the usual étale cohomology, which is that so singular cohomology, it's just vector space in some sense. But the étale cohomology comes equipped with a Galois action. So when we describe a cohomology, I not only have to say, it would be ideal to first of all talk about what the dimension of that is, and also talk about the Galois action. And for the H0, the Galois actions were trivial. With trivial Galois action. Whereas the top cohomology, the Galois action is minus X. So the Galois group of K acts by the cyclotomic character to the negative dimensions power on this one-dimensional space. Okay, so that's the only sort of difference. So, if you think about sort of topologically, right? X is of dimension X. Think of it as complex. Let me say dimension. Let's say dimension X then. Okay. So I have an n-dimensional variety over K. And think of it as in the complex dimension. So it's complex dimension n, so real dimension 2n. So if you have something compact at the boundary, then H0 is one-dimensional, and H2n is also one-dimensional. But the only difference is that the étale cohomology here comes with a different Galois action. The Galois action is given by chi cyclotomic to the negative dimension of X. So, in addition, if X is a geometrically connected curve, I always assume my X is proper and smooth. So this is a projective, projective smooth geometrically connected curve of genus G. Then as I said, H0 and H2 are given as so. But I want to say that the dimension of H1 of X of QL is 2G. Just like in the sort of, so what you learn in that probably algebra topology, right? A genus G, a Riemann surface, or a algebraic curve has the first sort of topological first cohomology being dimension 2G. Okay, so differences differences with singular cohomology. Okay, so let me list just a couple of differences between the singular cohomology and the étale cohomology. So first is that the singular cohomology has the benefit. This can have, maybe such that can allow z coefficient, whereas H1 étale only allows which over here, it also, so single cohomology also allow Q coefficients or any sort of base change from these. But when we talk about HI, étale cohomology only allows either torsion cohomology or ZL or QL. So you cannot, so this is one of the sort of issues with étale cohomology is that it doesn't have a sort of Z coefficient or Q coefficient cohomology theory. The coefficient is always either, well, actually when it was defined, one first defined it over the torsion cohomology, Z mod L to the NZ. And then we pass the inverse limit, get to ZL, and then invert L, get to QL coefficients. So that's basically the only small issue we have to pay attention to when we talk about étale cohomology. We can't talk about sort of Q coefficient étale cohomology. And another thing is that this étale cohomology has Galois action. And in fact, if you think about this, if you think about these two somehow, they work pretty well in the sense that if my étale cohomology had a Q coefficient, but Q doesn't have a topology, Q doesn't have a sort of Q has only discrete topology. And of course, if Q has discrete topology, if it carries a Galois action, that would be sort of Galois group mapped to GLN of Q. But that has discrete topology, and so we can only see finite representations that way. But of course we kind of know that somehow the Galois action on this étale cohomology should not be finite. So in some sense, the Galois cohomology, so the Galois representation on HI will have a large image, because when you see you have this going to GL of HI étale, right? So this is something like GLM of QL. So there's L-adic part, and over here there's some sort of L part, where the topology should be compatible with this one. So the image could be infinite. You allow the image to be infinite, I guess. So if this were having Q coefficient, this image wouldn't be able to have sort of infinite images. So all these discussions, I hope that I can, in some sense, give you some sense of what étale cohomology looks like and how to work with it. Now I want to discuss a little bit more about what kind of Galois representations we see in geometry. Maybe before that, let me sort of draw this picture. I remember I was visiting. I forgot. It was either Caligari or Emerton. I forgot who it was. So he was very happy that he pulled out a board where he said somehow Langlands himself explained Langlands' program on this board or something. And somehow, as Langlands sees things and sees his own program, somehow there are three parts of that's in it. On one side, there's automorphic representations. On the other side, there's algebraic geometry. On the other side, there's a Galois representation. Okay, so before that we've been talking about the Galois representations here. A so-called long-run program is basic to terrible position of three things. Anyways, is to relate these three together in some sense. So there are errors among them. The way how things works is really so basically, remember, I guess in the very first class when we talked about Fermat's last theorem. So the starting from the Fermat's equation, I get some Galois representation here, and I wanna show that I guess there's a way to go from this orthomorphic representations. So this is, for example, modular form. In case there's confusion here. So I guess before Langlands, there's a way to go from modular form to something in algebraic geometry. This is sort of talking about so-called modular curve. I'll do that next time. And taking Jacobian, so-called. And I get to some algebraic geometry object, and then going from algebraic geometry to Galois representations. That's what we're talking about today. So taking étale cohomology, and also maybe sort of talking about Galois actions on abelian varieties. So we have a way to go from algebraic representations to algebraic geometry and then to Galois representations. And what Wells proved is in some cases, this is Wells' work, one can kind of go back. Once you have this arrow going this way, he can somehow show that in some cases he can go back. So we've talked, before today, we've been really focusing on the Galois representation side. And now the goal of today is to explain how to go from algebraic geometry to Galois representations. And the general tool is to sort of use étale cohomology. Of course, in special cases, we can use Galois actions on torsion points of abelian varieties. Maybe I'll say that later. But today, I just want to give you a general picture of what kind of representations, what kind of Galois representation we can get from algebraic geometry. Okay. So the essential tool we're doing is that I take an x here. I take the hi, étale of x. Oh, another thing I forgot to say is that my x is over k. Whenever I write étale cohomology, I always have to base change it to a separable closure of this. At this moment, I just maybe you can think of it this way. So where does the Galois action come from? Because when you base change from k to k separable closure, the Galois group acts on the last factor here. Okay? So therefore, the Galois group will act on this thing you take called modulo O, and therefore act on the Galois cohomology. So that's why I always base change to the separable closure. And for most of the cases we consider today, we'll be base changing to algebraic closure. I'll just write a k bar here. But it's not going from algebraic geometry to Galois representation. Let's just take the étale cohomology. So let me explain in several cases of what kind of Galois representation we get by applying this étale cohomology process. And another reason I want to do this is because I want to explain, we discussed so much sort of about deformation spaces, and I want to know like which deformation has the chance of coming from something algebraic geometric. So 1k is finite. It's a finite field. I always assume x is proper smooth over k. So say k equals fq. And remember that I need my coefficient L to be not dividing the characteristic of k. So L is different from k. So in this case, this étale cohomology, now I base change to the algebraic closure of this finite field fq, taking q out coefficients. So this will carry an action of, again, this is sort of finite dimensional. vector space. Okay, so this will carry an action of the Galois group of FQ. And this is, we know this is a procyclic group, so it's enough to look at the action of the geometric Frobenius. So now basically I have a one operator acting on finite number vector space. So in this case, what we know is probably you have seen it before. This is what we know about this Frobenius action. This is so-called Weiss conjecture. This is proved by Delisle. It says the following: that there are several parts, maybe. Oh, let's write it this way. The characteristic polynomial I take determinant of x times identity minus phi of q acting on the ith étale cohomology. So I write it out as x to the n minus 1 plus. Save the trouble. Okay. So I look at the characteristic polynomial of the geometric Frobenius acting on this space here. First of all, this has z coefficients, namely, all these AIs are in Z. And note that this is a QL vector space. Okay, I have an operator on a QL vector space. Operator, all these AIs are in QL. But somehow when you really take the trace and all these sort of coefficients of the characteristic powers and polynomials, they're all in Z. Secondly, this characteristic polynomial is independent of the prime L. In the sense that we can, so when we talk about étale cohomology, right, one of the issue with étale cohomology has to work with some QL coefficient for some prime L. There's only one constraint where L is different from P. So priori, of course, the vector spaces are different. For QL and QL prime, they're different fields. So therefore, vector spaces over these QL and QL primes are different. But if you look at the Frobenius action on this vector space, the characteristic polynomial is independent of this prime. Thirdly, maybe the first one, but also it tells you that roots are all algebraic integers, because all the coefficients are integers. So for n is 0, alpha of this characteristic polynomial, well, it's in Q bar, and any embedding QL bar into C. Let me call it infinity. So, I mean, of course, alpha lives in some sort of finite extension of Q. Okay, choose for any embedding of this sort of algebraic field into C. Then the sort of norm of this alpha is precisely Q to the I over 2, where I is the ith cohomology, the I we take here. So give it a name. So I'm going to call such alpha a way Q to the I over 2 number. that's basically what they improved and what we conjectured. So the essential part of this conjecture. But there's still a tiny bit of this thing that's still. Oh, so this is proved. So this is a theorem. Just in case it was not clear, this was the theorem. Okay. So this was because it was called Wei's conjecture, but it was proved by Lin. So it's a theorem now. But what I state now is a conjecture, and I think it was conjecture the VQ action on the tau cohomology is semi-simple. I.e. no Jordan blocks. So it's conjecture that this is okay. I have a operator on a finite vector space, and anything coming from geometry shouldn't have some sort of very straight situation where this Frobenius action has some sort of Jordan block shape. That shouldn't happen. It should be always diagonalizable. The Frobenius eigenvalues could be same, but yeah. Okay, remark. So I didn't have time. I don't think I will have time to talk about Lepsich-Tritz formula. I think all this discussion can be found in, for example, I think. I'm not sure. I would believe that has shown. Appendix A has a good account of all these discussions here. It was one of the appendix has a good account of where he talked about a little bit about Sir Wei's conjecture. So this has something to do with using this we can count the number of rational points on X in the following way. So if I denote alpha alpha 1 1 alpha what do I want? Alpha 1 I, alpha R I. If this denotes the B eigenvalue on HI tau of X. So if we write down all the eigenvalues, of Frobenius action on the étale cohomology, then for all I, but I only have to go up from 0 to twice the dimension of X, because that's where this étale cohomology is not managed. Then for any M, I can look at how many, my X is defined over FQ. So I can look at how many points I have over an extension of FQ, namely F to the Q to the M. So this is, let me write it this is you sum over all the cohomological dimensions, and you sum over all these roots of this number. There's a sign times alpha, hold on a sec, I, J, to the nth power. Okay? So let's give an example. This is slightly complicated notation to follow. So here's an example. Say X is a curve of genus G. So when I write curve at X, I always mean proper smooth already, a geometrically connected. Okay, geometrically connected. Okay. Then we know that somehow H0. Oh, every time I have to write this. This is QL, and this is a trivial action. So therefore, I get sort of alpha was get 0. The first eigenvalue for degree 0 is 1 because the action is trivial. And H2 is easy. QL minus 1. So the top cohomology always QL minus the dimension. And what's the Frobenius eigenvalue on this one? For cyclotomic character, the geometric Frobenius is set to Q inverse. Now I have the inverse of cyclotomic character. So therefore, the first eigenvalue in degree 2 has Q. Eigenvalue is Q. Okay? And H1, this one has 2G dimension. So now I have alpha 1, 1, alpha G 1. Okay? Where now I can use the least Weiss conjecture to bound each of the numbers here. So each alpha I1 has absolute norm less than, being precisely equal to Q to the half. So that's what Weiss conjecture says about this particular case. So what do we know about sort of rational points on this X? So XFQ must be equal to, well, you have to sum up these things in some sense. Well, let me start with Q. That's okay. I think adding the M wouldn't affect too much. Okay. If you're not happy, just assume M being 1. Okay. You have to sort of sum up these things. So for degree 0, I get just 1. 1 to the M is just 1. And for degree 2, I get Q to the M. So these are the pluses, where this sign is plus. And then I have minus signs for the degree 1 terms. So minus, ouch. So let's remove these. Okay, fine. I just feel like the notation's a bit awkward. Like that. And what can we get from this? Oh, sorry, number of elements. Yeah. So what can we get from this? So roughly how many rational points on X do we get? Well, a corollary of this is that if I look at the number of rational points, somehow the two leading terms are 1 and Q to the M. For the rest of the terms, we know that they have absolute value being exactly the root of Q. So this is less than equal to 2G times Q to the M over 2. Okay. So if you somehow imagine that Q is relatively large, it's just take M equals 1, right? Q is relatively large. Then that sets the number of rational points on this X is roughly 1 plus Q times the error term, which is about the size of root of Q, times the genus of the curve. So that's what Weiss conjecture tells us. Okay, so now let's move on to the next case. When K being QP, before it was a finite extension of finite field. Let's see, what do I want? Yeah, let's just take it to be a little bit more general. Excuse me. Oh, okay. Maybe K is a finite extension. Finite an extension of QP. Okay. But then I want to note that when I take K to be finite extension of QP, this K has characteristic 0. It does not have characteristic P. Okay. So we allow L to be P. This is allowed. But I will separate several cases to discuss. First of all, let's consider case L not equal to P. And I want to assume that X admits a proper smooth model over the range of integers of OK. The range of integers OK. So in other words, I can find an X which is proper smooth over spec of OK, whereas fine, K, small k, big K. So let me write small k equals big K. Okay, and the residue field of this big K is, say, FQ, as before. Okay. So maybe I should. Of course, I can find this. Let me put it in a little bit middle. Okay. So what I mean by X having a proper smooth model is that my X can be extended to something proper smooth over the integral. Okay? So think of this, right? And once I have this, I can talk about the special fiber of this one. Okay, sorry. So this is a Cartesian pullback of this. So I could talk about the generic fiber here, which is variety over capital K, and have a special fiber of this, which is the proper smooth variety over a finite field. Now there's a natural question to ask, how do we compare the étale cohomology of these two? So in this proper smooth case, these two are comparable. That H2 étale X of K bar QL is isomorphic to HI étale cohomology of X Q bar QL. So these are isomorphic. So both sides have some Galois action. This side has this Galois group of K acting, and this side has a Galois group of the finite field acting. And this isomorphism is compatible with this isomorphism in the following sense that, you have a Galois group, you have an element in the Galois group of K, then you can look at how it acts on a residue field, right? So I have a map going this way. So this isomorphism respects the corresponding Galois action. In particular, this will tell you that the Galois action on this is unramified, because all the Galois action here will actually factor through the Galois action of the residue field. Sorry, I should have read it a little bit higher. So let's go up a little bit higher. I want to stick it in here, and because somehow, although I have some sort of X has although I'm thinking about the cohomology of a general fiber, if it has a proper smooth model, then the étale cohomology is the same thing as a special fiber. And therefore, I can use the weight conjecture and say not only this scalar action on this general fiber étale cohomology is unramified, and the geometry for this eigenvalue are way or what did I say? Did I say way q? I'm not so sure the order of this. Q to the I over 2 way number. And the eigenvalue are independent of L. Okay. At this moment, I'm not allowing L to be equal to P. When we talk about this, of course, we should expect the Fourier action to be semi-simple, but that's nobody knows how to do it. So essentially, the case when this X has a proper smooth model, namely has a good reduction, or somehow so-called good reduction case. When X has good reduction, things are very nice, just like the finite field case. Sorry. Next, I want to talk about case 2, where L not equal to P and X general. Oh, I'm a little bit worried about this. I want to assume X to be projective, but maybe this also works for proper. I'm not quite sure. I mean, the difference is really tiny for our consideration. For most of the cases, I guess we'll be mostly working. I mean, for most of the cases, the variety, if it's proper, it's probably usually projective. Of course, there are counterexamples. It's proper smooth over spec of K. Okay, so now what we see is that we genuinely have a Galois group acting on the étale cohomology. And if X doesn't have a good reduction, it's usually ramified. Remember, in one of the videotaped lectures, I said at least for abelian varieties, H1 being unramified will imply that the variety itself has a good reduction, but this is not true in general. So therefore, it may be happen that F doesn't have a proper smooth model, but scalar action is unramified. So in this case, so let me tell you what is expected about this. So in fact, this is a corollary of a conjecture. So it doesn't matter, still a conjecture. So-called weight monodromy conjecture. I guess this is now, due to Schulze, known for, hold on a second. Yeah. This is now known due to Schulze that it works for all the complete intersections inside Pn. Global complete intersection inside Pn. Anyways. So X. So okay, I have a, what do I have? I have an L-adic representation, and I have a sort of Galois group of p-adic field acting on it. So we discussed in probably the second or the third lecture that associated to such thing, we have a Grothendieck's monodromy theorem that we can associate weight Deligne representation associated to such representation. Always. It says that, okay, let R and V denote the weight Deligne representation. What that is that maybe I just kind of quickly remind you what that is. So that's just sort of R. So it's a representation of the weight group going to GL of V, and N is an endomorphism from V to V, such that I guess R of the Frobenius inverse N, R Frobenius equal to Q times N. Okay. So that's what the weight Deligne representation is. And maybe I just mentioning here, a key property here is that somehow the image of inertial subgroup is finite. Somehow over here, the time inertia here may have a ZL part. It may act on the space with infinite image. Associating a weight Deligne representation will take out that sort of infinite image part and replace that with this monodromy operator N. Okay, and therefore we get sort of a representation which looks like a lot like a sort of finite image representation, in the sense that the image of the inertial subgroup is finite, and also there's a monodromy operator captures sort of the infinite part action here. Now, then once we've done this, because here's something. So let me write it down. The first statement that this is independent of L. So before passing to weight Deligne representation, this Galois representation over here cannot be independent of L, in the sense that for different L, the image here should be has a large part of sort of ZL in there. For different L, ZL cannot be compared with another ZL prime. But the way this ZL is sent into here is that somehow over here you have the so-called time inertia element T here, right? Tau, where tau is basically roughly belongs to a subgroup which looks like this inside here, right? Inside here, and then this tau has some sort of usually unipotent image, something like this, for example. We don't quite compare this full Galois representation here, but we only pick out the generator of the time part when it maps over here, and then this is sort of the, let me say, call it rho tau here. The n is kind of like the log of rho tau. So I remember I guess I remember the operator. I guess remember the time action by remembering how the generator act, and that's some sort of more algebraic things I can compare for different L's. So the first statement is that this weight Deligne representation attached to this étale cohomology with the Galois action is independent of L. So in fact, what the trouble is proving this weight monodromy conjecture is this n here. If n equals 0, I guess maybe for one of them, if n equals 0, I would imagine that. Not so sure. Sorry, I take it back. The trouble is the n here. Without the n, this statement is sort of essentially okay. Secondly, this is a bit long, but let's write. So S sort of V inverse and phi equals great sense of time. Okay, leave it to the next one. Okay, so let's continue. Right. So just recall what we had. So we have some k finite extension of QP, and have x projected smooth variety over k. And I'm taking the hi of this, and I can take this ith cohomology, turn that into a weight Deligne representation. And the weight monodromy conjecture, or rather a correlate of that, first of all states that this associated weight Deligne representation is independent of L. Secondly, this is something called purity. So let me sort of state it. So let's first of all recall that my phi is geometric Frobenius. Maybe just write phi. Phi inverse and phi is Qn. And then if you look at what this means, this means that n will sense sort of phi equals alpha eigenspace to phi equals alpha divided by 2 eigenspace. Hopefully I got it right. Wait. So let me double check. I'm a little nervous now. So okay. So what do I have? So I have n phi being Q. One more time. Right. Yeah. Okay. So n phi being Q phi n, right? So this. So therefore, if you have sort of Q equals alpha eigenspace, you apply n. So let's see. Say dv equals alpha v. Then I do n phi n of phi v. What am I doing? Okay, sorry. I do n. So if alpha is in the phi equals alpha eigenspace, now I want to understand what phi n phi is, right? Sorry, Q. This is Q. What is phi n phi is? So Q phi n is 1 over Q n phi v, right? And phi v is alpha v, so this is so alpha here maybe. So it sends phi equals alpha eigenspace to phi equals alpha over Q eigenspace. Okay. So nonetheless, you see that this monoidal vector will send one eigenspace to another eigenspace, and the value of this eigenvalue will be divided by n. So, but this will never come back. I mean, you divide a number by Q, but this is a finite number vector space. There are only finite many eigenvalues. So this will imply that n must be nilpotent, because after you apply n many times, it will be divided by so many Q to the m's. It will be outside of the sort of the set of all the eigenvalues. So therefore, n, whatever that power is, will kill the vector. So n must be nilpotent. So here's a general fact, algebraic fact. This is usually called Jacobson Morozov. That whenever you have a nilpotent operator on a finite number vector space, you can somehow extend this nilpotent operator to an SL2 action. And I think if, in particular this particular case, if n commutes with the Frobenius action, you can somehow make this sort of compatible with the Frobenius action in some sense. So this V can be decomposed as the direct sum of the following. Given a name. So I'm gonna do a big diagram somehow. Here I write P. So I is the ith cohomology to I here. So I want to write I plus what I want to do, maybe M. I want to take, I mean, because n is nilpotent, essentially I want to take some sort of Jordan block, right? And then I would have some sort of a longest, I guess, sort of chain of. So remember, like, so if n is some sort of Jordan block, like, it's nilpotent. So if I have some sort of long Jordan block like so I will have, I guess, the first vector being what I have over here, and then I do n, I will get to the next vector. Or maybe this expression is terrible. So I want to write my n as the direct sum of 0, 1, 0, 1s. So this is size m to direct sum with some r m's. Okay? it's a new polynomial operator. I can write my n as direct sum of Jordan blocks, right? So the way I write each of the block for each m, maybe m, okay, m from 0 to m0, say, okay? So let me write m0 here. And this has dimension Rm0. And the direct sum of all I'm going to write here will be the direct sum and over there where m equals m0, this block. So n will send the first vector to the second vector to the third vector and so on and so forth. No. I don't want to write this like that. So n goes to the end of this. This goes to n square of oops. Sorry for so if I do n here, it's going to go to 0. Okay, so it's the first direct sum that I have over here where m equals m0. I essentially draw the Jordan block where n actions I'll take this to the next. But think about these as vectors, right? N of the first vector gets to the next vector, n of that vector goes to the next vector, and so on and so forth. Okay, so that's m0 and m1. So I do things in an aligned way. Okay, so I deliberately write this in the middle here, I plus m minus 1. So n of p I m minus 1 square p minus m 0 minus 1. Over here, I apply m0 minus 1 time I'm going to align it into kind of a triangle like this. Okay. Oh, I is this. I degree. So I doesn't have, but I have a reason to write it like so. Okay. Just you can for the decomposition you can ignore the I, but I label things for a reason. Okay. So okay. So let me suppose that I just have one block, okay? So suppose that I just have one block. Okay, so this vector is so now I have bases, right? I have E0, E1, E2, and so on. Then this is vector space with bases E0, vector space with bases E1, vector space with bases E2, and so on and so forth. Suppose I just have one block, and I write the bases like E0, E1, E2, and so on. This is a vector space with spaces U0, vector space with spaces U1, E2, and so on. The n will send this to one to the next. Okay, now I take m equals m0 minus 1. I get another chain. But align it in such a way that this, or at the moment they don't align. This is in the middle of these two. And minus 2 here. So this aligns with this. So over here I have n. Okay, and at the very end, right in the middle somewhere, I put pi, or just by itself, and this n here is 0. about how you write Jordan blocks. Look at this. And the what did I write here? I wrote something here. Just 1 second. So the kernel of n, if you want to know. So the last bit here is the kernel of n. Okay. Makes sense. Okay, now I'm going to explain why I want to make these troubles do this. Of course, I want each pi to be phi stable. This is built into Jacobson-Morozov theorem that we have, especially when n sends this eigenvector to the other eigenspace, then you can definitely make these chains. That's okay. Just by looking at the nilpotency of this this operator n. But then, what this part says is how the weight monodromy conjecture says that the phi eigenvalue on each, I guess it's enough to just write it on p, but anyway, so let me write it in more general. Nj p I plus m are q to the half of, somehow the weight is I plus m minus 2j weight numbers. Okay? So the minus 2j is not surprising because whenever you hit it with n, it'll be divided by q. So, I mean, when I state sort of the conjecture, I don't have to say this. I just need to sort of see where this p, say how the x on each of the sort of primitive parts. P stands for primitive, sorry. And but somehow the statement is that so this here. So vertically, I'm aligning all the sort of q to the whatever weight numbers. For example, over here, it's always q to the half of I plus m0 minus 2 weight numbers. For this one, it's a primitive, but the other one is I plus m0 minus 2. So for that sort of weight number. So, for example, over here, so let me actually use the concept of weight. So whatever the number put here is called the weight. So over here, this is sort of weight I plus m minus 1. So this is weight I plus m0 minus 1. Over here, this is weight I plus m0 minus 2, and so on and so forth. And what this weight monodromy conjecture says is that the entire cohomology, when you turn into the weight delimitation, is somehow centered at weight m0. Oh, excuse me, it's centered at weight I. My bad. Sorry. I.e. the picture. I.e. all n chains are centered at weight I. That's what the conjecture says. Okay, then m0 plus 1. Sorry. Yeah, you're right. You're right. Awesome. Very good. Very good. Sorry. Yeah, of course, I can't have a 0 times 0 matrix. Very good. Yes. Right. So there's a name for this. It's called so this is called pure of weight I. But when they say pure of weight I, they do allow a this monodromy operator n. in that case, it's not sort of each of the space having not sort of each of the space are q to the half of I over 2 weight numbers. It means that you have this sort of diagram here. All the n chains are centered at q to the I over 2 sort of numbers. Okay. Maybe another comment is that when we go back to the good reduction case, where n equals 0, we're only left with this last one here. In case n equals 0, so we only have the last piece here. So good reduction case really says that this pi here has weight I. That means that the appropriate eigenvalues are weight q to the I over 2 numbers. You just write it down here. So this is a general picture here, but then in this case, we weight the linear representation of it's just this representation itself. In this case, it doesn't change anything. And with the Frobenius action, and n being 0, and therefore, as we discussed from the weight conjecture, that is somehow the phi eigenvalues are what I'm trying to say, are q to the I over 2 weight numbers. Right. So any questions on this? So if I'm not mistaken, so each of the PIs, I mean, remember there's not only for geometric Frobenius, there are other sort of elements in the weight group. Each of the PIs I can take to be a representation of the weight group, sort of stable under the weight group action. You can take decomposition cell. Okay, no question. Let's move on to K3. For K3, I'm going to do a L equals P situation. But in this case, for K3, I'm just going to do K equals QP, and L being P, and X proper smooth. Over ZP. So as before, this still makes sense. So after étale cohomology, now I have QP coefficient. But QP has characteristic 0, so still can talk about QP coefficient étale cohomology. This one carries the Galois group action of QP. But, maybe I should say but. So X bar, FP bar, this makes sense. But this doesn't. Well, this is, I guess it's badly behaved. I'm not so sure this will even define. I'm not so sure. Okay. My understanding is that whenever talking about étale cohomology, avoid the case where this coefficient P is equal to the characteristic here. Okay. But I think it's still, maybe there's still definitions. I'm not so sure. Okay. Let's just not talk about it. So let's not talk about it. So you can't quite compare that with this, in the analytic situation, compare that with this one. But in the sort of recorded video lectures, this is a crystalline representation. So let me write it as HI because it's a little bit long. So we've discussed from last time that from these recorded videos that I can define some sort of decrease of HI with a phi action. So the dimension of this one, which is the dimension of decrease of HI, is equal to the dimension of HI. And just as I said earlier, so just pretend X is a usual complex variety, and take the sort of usual Betti cohomology, and this is what intuition for what HI would look like, and the dimension of that would look like. So this is some sort of finite dimensional vector space, but equipped with a phi, which is maybe I should say crystalline Frobenius. Now here's the theorem. That first of all, the determinant of X times identity minus phi, this crystalline Frobenius phi here, acting on this decrease of HI, is a polynomial with integer coefficients. And remember that for L-adic cohomology, we talked about independence of L. This one you can do that as well. And this is equal to the determinant of X times identity minus the crystalline Frobenius. Excuse me, the geometric is on the étale cohomology of other coefficients. Of QL coefficient, étale cohomology, for any L not equal to P. So earlier we said that somehow this étale cohomology here, which is the same thing as étale cohomology of the special fiber of X, which is independent of this L. Now what I'm saying is that there's also an independence of L for p-adic coefficients. But it's not about the sort of Frobenius acting on this space here. It's about when you have this space, you take so-called decrease of that, which carries a crystalline Frobenius. And this has the same dimension as this HI, and then you take the characteristic polynomial of this one. That's the same thing as the characteristic polynomial of the usual Frobenius acting on the L-adic coefficient étale cohomology. In the sense that somehow, I guess you could really think of decrease of HI as a p-adic replacement of étale cohomology. So that's, I guess, how we should think of these things. And because of this identification, because of these identifications, all phi eigenvalues are p to the I over 2 Wade numbers. Okay? And again, it's conjecture. That the phi action on this decrease of HI is semi-simple. Of course, not known. Just add a tiny bit of something I like to consider personally. So we know that all these phi eigenvalues are p to the I over 2 Wade numbers. So that's the sort of absolute value of these phi eigenvalues. But now these phi action on the decrease, I mean, this is a QP vector space. You have an operator. And it's very natural to consider sort of p-adic evaluations of these sort of Frobenius eigenvalues. So the question is, it's an interesting question. What can one say? about sort of VP of phi eigenvalues. So we can show that these are between 0 and I. Not known. I mean, in general, it's an interesting question. So these sort of PID evaluations, put them together, form a so-called Newton polygon. And later on, I'll talk about Hodge polygon. There's Newton above Hodge. Just a second. Okay. And also, in the recorded lectures, we discussed there's a canonical isomorphism between decrease of HI with the Ram cohomology of X. So this one is a filtered QP vector space because it has the de Rham filtration on this, the de Rham cohomology. And then, so therefore, this filtration will give a filtration on decrease of HI. Just kind of recall that the Hodge-Tate weights of decrease of HI are precisely J with multiplicity Hj of X omega I minus J. Oh, sorry, dimension of this. If you look at sort of Hodge theory, the dimension of this Hj of I omega I minus J is precisely correspond to the sort of Hodge. It's Hodge weights. That's basically what this filtration says. The gradient piece of this filtration is. In a second. Let me erase it now. So this is because take the filtration. The J's filtration of this is precisely Hj of X. The reason I state this Hodge-Tate weights statement here is because I want to remark that later on we're going to consider X over number field. It will have different primes P. When we talk about sort of QP, where the P can also change. And then in that case, the Hodge-Tate weights will be a dimension of some sort of Hj of X omega. So this will be some sort of fixed number that doesn't change as P changes. At this moment, X is over QP, but if I take X over Q, I can, consider sort of QP theory or QP prime theory. When I consider QP prime theory, these dimensions will still be the same dimensions. So therefore, the corresponding sort of decrease for P prime, the Hodge-Tate weight of that will be the same for this. Getting close to that. Oh, I'm not going to do this again. I really want to the end. So if A over AP is an abelian variety of dimension n, then for talk about H1. For H1, then I can talk about decrease of H1. So this is sort of 2G dimensional space, and and the phi action here, the phi eigenvalues, if you take the absolute value of that, it's always root of P. Just like in the étale case. So the phi action on the crystalline cohomology So have the absolute value of root of p. And the Hartree weights are, well, are these sort of degrees. So therefore, it's basically 0. You have n times. And 1 n times. So Hartree weights are just 0 and 1. Each has multiplicity n. Or I mean, I can take, or alternatively, I can take curve. Same thing. Slash curve or curve C of genus. And they have this. I mean, essentially, they have the same H1. I should have done that. Case 4. Don't talk about general K. General K, sort of finite over QP, and X proper smooth over K, and L equals P. I'm not going to say too much about it. So in this case, the Galois group of K would act on the HL cohomology of K bar QP. Oh, small k. And there's a way, let me just say it. There's a way using p-adic Hart theory. Since this is not a course on p-adic Hart theory, let me just sort of gloss over this, to attach a weight Deligne representation to this HI. Just like over here, I take some decrease. Right? Instead, I take some sort of D semi-stable version of this, and up to some profound extent, so-called D potential semi-stable of this. And that will give us a weight Deligne representation. And it is conjectured to be equal to the weight Deligne representation of HI of the same thing, but with L-line coefficient. But of course, it's just a conjecture. So in other words, I hope that I stated all these conjectures and sometimes theorems. I have to sort of convey to you some sort of local in the global things, in the sense that, of course, we take cohomology using different coefficients. At the end of the day, we can sort of recover them as just one thing. There's only one sort of space where the cohomology should have one sort of particular property that's governed by this weight Deligne representation. Now, that KBQ and X proper smooth. Or maybe I should say projective, just in case. Variety over Q. Now for each L, I can talk about HLI X being this étale cohomology with QL coefficient. So this carries a Galois group of Q. Whatever field you put here, you put down. And I'll have to have both Q and L come into play. For each prime P, So I have this, I think of this as a kind of a Galois representation, which is coming from the ith étale cohomology of this X. And I restrict that to consider the action of the local Galois group of QP. And this is precisely the same thing as we somehow, first of all, base change X to the local field QP and have a closure, and then take the étale cohomology. And with, of course, this will automatically carry this action. So all our earlier discussion can be applied to where if my X is defined over a number field Q. So therefore, this space here enjoys all the local, all the sort of good properties we considered earlier. So then, let me first of all throw out the concept, and I'll discuss what it is very precisely. I say, okay, for all these things, this collection of this HI, of this for different L's, this forms a compatible system of Galois representations, as defined as follows. Okay, so you see, as we talked a lot about independence of L. So now, if I take different L primes here, so this will form a kind of a compatible system of Galois representations. So here's the definition of what a compatible system means. So take the time, but let's see. So let L be a number field. So far, I've been talking about QL and QP coefficients. I mean, in general, I should allow more general coefficient fields. So my coefficient field is basically L. And for each prime lambda of L, let rho lambda be a Galois representation. So suppose for each prime lambda, I have a locally I have a lambda-adic representation, just like the L-adic. Just think of L equals Q, and then I have some L-adic representation. But for this definition, it's better to assume this representation to be semi-simple. If it is not, then you take semi-simplification. A. Say that we say that this collection is weakly compatible if you can find a finite set of places S of Q such that so this is basically the ramification set such that if P is not in S and my lambda is my coefficient is not sort of Pi the coefficient, then rho lambda is unramified at P. So in other words, the ramification can come from two things. Either it's because it's in the ramification set, or it's possible that my prime P it happened to be this L. So for that lambda-adic representation, that P, that L is not sort of well, it's usually not unramified. And so for P is not in the ramification set. If P equals to the coefficient characteristic, then it's also likely to be ramified. So I can assume that. So that's unramified. And in this case, I can talk about characteristic polynomial of rho lambda of Frobenius at P of X. So this characteristic polynomial a priori it lives with this coefficients, but I require to have coefficients in just L, purely L coefficient, and this is independent of lambda. So independent of what sort of coefficient you choose here. So that's definitely weakly compatible, just basically sort of minimum requirement in some sense. These traces or this characteristic power system of this Frobenius element is independent of the coefficients at lambda. So this is what's happening for sort of varieties in some sense. So B. So basically, we're going to define weakly compatible system and compatible system and strongly compatible systems. So of course, we know that somehow the varieties form a compatible system. So that's what we're going to define now. So we call a weakly compatible system. So lambda compatible. The following four conditions holds. For any P such that lambda divide P. So at where this I want to reduce to a Galois group of QP, but if P is sort of same thing as lambda in some sense, reduction, excuse me, the restriction, rho lambda to the local Galois group is so-called the ROM. I didn't really define what the ROM means, but somehow I just want to point out that Chrysalin implies the ROM. So we're talking about this Chrysalin case, but of course I have to do a general situation, so it's the ROM. And anything from geometric is always the ROM. Okay. I mean, for many cases, sort of, it's good enough to just imagine this ROM is the same thing as Chrysalin. Once again, for any P, at P equals P case, the set Hofstadter weight of this the ROM, again, just think of it as Chris, of rho lambda restricted to the Galois group of QP. This is independent of P. So this follows. From our earlier discussion that at QP the Hofstadter weights are precisely given by the dimension of this sort of H, some J of X omega I minus J, right? So because this is so for J as multiplicity, so dimension of H, J, X omega I minus J, right? But this is something. So this is something over Q. I mean the dimension of this is some sort of Q vector space actually. So for different P, when it tested with QP, we'll have the same dimension. So therefore, this set here is independent of this P. Thirdly, if P is not in S, so again, so all these additional conditions are at P. So A says P not equal to L condition, so this is at P condition. also L equals P situation. If P is not in S and lambda divides P, then if we were talking about analytic situation, this would be unramified. But now we're in a p-adic P and P situation. So I should replace unramified by crystalline. And as before, the determinant of x times identity minus phi is phi on decrease Vp or crystal convenience restricted to the color group should be equal to other things. Lambda prime. As I said earlier, so if the corresponding thing is crystalline, then the characteristic polynomial for the crystalline Frobenius should be the same thing as characteristic polynomial for the L-adic representations. So this is sort of another sort of independence of L, but somehow now include the P case in. Lastly, so these three are somehow considered the case where L equals P, basically. The last case considers the case where P equals infinity. Let C be a complex conjugation. Then trace of rho lambda C. I mean, this is all automatic, but this is independent of lambda. So the complex conjugation is, in the GL2 case, basically, is either identity or 1, negative 1, or negative 1, negative 1, right? But then I have so many representations with different coefficients. I want them to be compatible. They have to be all of sort of the same form. Any questions about these? The important thing is learn to spend time cleaning the board while you look at it. So the way, I guess, the way how things are defined is the weakly compatible is to talk about the conditions when P not equal to L. For it to upgrade to compatible, you add some condition where L equals P and P equals infinity. And also, I want to define C is strictly compatible. Is strictly compatible. This is the condition that we hope to be true for any geometric situation. Basically, it says that for any P, the Frobenius semi-simple associated weight-delete representation is independent of lambda. Sorry, let me add a couple. Quickly, 1 minute. So if X projected smooth over Q, then HI etal QL semi-simple is a compatible system. Over Q. And if X is an abelian variety, over Q, then strictly compatible. Of course, it's a conjecture that weakly compatible will imply compatible and imply strictly compatible, but that's something very difficult to prove. Okay, I'll stop here, and next time I'll pick up from here.